Okay, so we start again. Thank you for being there and putting up with all this. So the plan today is more or less the same as the previous day in terms of schedule, so 55 minutes break and so on. So we're doing positive elements. This is what we left off yesterday, and we call that class is a set of A and A, that A is positive, and this is the same. Y in A, and for all these guys, we have that existing Y. Right. And all one square root. Okay. We also write the positive in this. The positive, no surprises here, and A, B are joined, so elements that are equal to their joint, then we write A, B, if B minus A is positive, which gives a partial order on this set of self-adjoint elements. So I didn't say much what that is. That is kind of, well, it's defined by this, though. This is also the same that they self-adjoint on the spectrum in the groups. Okay, so some useful things about this. So consequence, what we did last day, which is included in these definitions, is that already A in a unital algebra or the unitization, which I will talk about a bit later. This guy is invertible. And this is just functional calculus because A star is positive. So because of this characterization here, and by functional calculus, look at the system algebra generated by this guy. And one thing would be the continuous functions on the spectrum A star. So A star agrees with this element. So that will be A star. And A star plus 1 is here. So that has to be invertible. Okay. So that's nice use of functional calculus. And some other consequences of positivity. Some of them are easy. I will just mention them, and it's just kind of fun to have these things, but they come useful. So the first one, so if A and B is joint, A is equal to B, and if N is C, then C, A, C star is not equal to study B system. Okay, why is that? Because A minus A is positive, so how do I write this? Yeah, let's say B minus A is X star because it's positive, yes. So when you do C B minus A C star, this is C X star C star, and this is CX star, which is positive. So C B C star C A C star is positive. So it's one of the things. Another thing is that if A is equal to B, positive elements, then the one A doesn't equal to B. This follows from functional calculus. The thing is that if A and B are positive elements compared like this, and we know that they are invertible, then the inverse is less than equal to x. And well, to show this, let us check that part. So first thing is that observe that if an element greater than 1 and C is invertible, then the inverse is less than or equal to 1. That's just again by functional calculus. Okay. Now, if we know that this happens, if we know that it's a B, we can multiply by so A is invertible, therefore the square root of A is also invertible, so we can multiply by the inverse of the square root of A on both sides, and this is less than or equal to this thing. This is divided by 1, and this is just A square root times A square root, so this is 1, and by the previous part, we get that the inverse of this is less than or equal to 1, right? And the inverse of this is just the square root, the inverse A square root, and from here multiplying by, again, the inverse of the square root, we get this thing here. So that would be roughly the argument for 3. 4, that takes more work, so I won't do it. So if we know that we have comparison like this, then square root, which is was positive, the square root of A is less than or equal to the square root of B. So if A is less than or equal to B, for positive A, the square roots also compare. And more generally, any power which is less than or equal to 1/2 has this inequality positively helps. This A beta is the functional calculus. Okay. And one might be more optimistic and hope that it's also true with powers. So that's not true in general. So it's not true. That to be, that implies A squared doesn't B squared. In general, this is not true. And there's an easy example for this. Well, you can take to like two matrices, to like complex numbers. P the E11 corner with Q this guy, and then P is less than or equal to P plus Q, but P squared with this P is less than or equal to P plus Q. squared. That's one example. What is true is that if this inequality, I mean, if this statement holds for every A and B, and that's a result, I think it was proved by Ogasawara or something like that. Sawara, I don't remember the name. I don't remember the year, but this guy proved that if this implies this, whatever it will be, in A, then A is mirror. So it is true in the limited case, but not true in general. Okay, so these are some facts, and yeah, so we'll go back to positive elements, but I had to squeeze one of these big theorems that we won't prove, but somewhere it has to be. So and talk about the GNS representation. So GNS is for the alpha landmark. So this is I just state the theorem. So if there is a system algebra, then one can concretely represent A as a non-closed system algebra over Hilbert space. So there's this Hilbert space and an isometric representation. Right. So yeah, I mean, one can show this, but it takes a while. We have to talk about states and things like this that in principle I will not do. But it's very convenient because one can always view any system algebra inside V of H. And sometimes this is, I mean, sometimes many times this is done because in V of H we have like additional structure. I mean, it's what is called a Boltzmann algebra, and then you have more things you can do there. Polar decomposition, for example. So if we come to it, we will use it. Okay, and yeah, so something that appeared last day, and maybe it's useful to discuss a little bit. I wasn't really planning to, but of course, because of K theory and because also of the Kuhn semigroup, one needs to deal with non-unit algebras almost all the time. So maybe we should include a brief discussion on on unitizations and what happens when you add them. So you have a system algebra and a close to side ideal. For example, that's a main case where you have this. You have another system algebra which is non-unital, or we will have also later what is called hereditary subalgebras, and these are also system algebras and non-unital. And of course, one has the stabilization, which is also non-unital, and for many things one has to unitarize. So let me just define this. Unitization. System algebra is unital system algebra with an embedding A inside B. Well, let me put it like this, just for shorthand. I'm writing of this sort. This means that A is a two-sided, close two-sided radial of B. It is also essential. And essential here means that A intersects non-trivially any non-trivial ideal of B. Okay. So now the proposition here is that if A is infinitable, then there is a minimum unitization, which we call A tilde, and it satisfies when the quotient out. So A is not an ideal of A tilde, and it's the quotient gives us the complex numbers. And well, how do we prove this? Well, proofs are always sketchy. Sketchy in the sense that it's a sketch, not in the sense that it's not working. So I hope it will work. So we can, let's say, from A to the boundary operators on A as a Banach space. So A is a Banach space. You can take the boundary operators, and we can view A inside B of A as the right multiplication or left multiplication. So we take A and A to the operator that is A to AX. So that's left multiplication. So this iota is an isometry. So it's kind of fun to check this. So iota is an isometry. So iota of A with this applied to X. This is by X. And this is a norm inside of A, so that's less than equal. A and X, so that's easy part. I mean, everything is easy, but and on the other hand, the other way, the norm of this applied to X. Sorry, the norm of this thing is, I mean, it's the supremum of the norms of this map applied to every element from 1. So in particular, it's greater than or equal to the idea of A applied to A modulo this norm of this. Okay, if A is non-zero, if A is 0, everything trivializes. And this is equal, this is by definition, A star, variable A star. And by the C-star equation, this is okay, so that implies that iota is an isometry. And now we let A tilde to be the image of A together with the complex numbers times the identity inside of here. And now one takes the norm induced from here. From the and evolution like that. And that then one checks that A tilde defined like this satisfies everything. So yeah, so I didn't do all the details, but this I So let us observe. So we can still have some space here. Let's observe that in this definition of the unitization, we can the product goes like this. So I have A plus lambda times identity times I of B times mu. How does that product go? This is, I mean, you multiply as you have to, right? I mean, you have B plus lambda of B plus mu of A plus mu. So that's the order of some guy. B plus lambda B plus mu A. So that motivates, or you can use this as a motivation to define fine in general. Plus, for any complex algebra, actually, you don't need to have a sister algebra for this. A times C, just the Cartesian product, with component-wise addition and with some with a product. Like we expect. A plus A. Which is complex algebra that contains with unit is this thing, and it contains A is so to say the other. Oh. Yeah. And this is still the complex numbers. So this A plus is very convenient to work with because it's very explicit. Only from A I'm taking the complex numbers. One doesn't have to put A inside these operators. So A plus can be identified with A tilde whenever you don't have a unit. And otherwise, it's the direct sum of A and C. So I can summarize this maybe here. So what is the relationship between A plus and A tilde? Well, A plus is a sum of A tilde if A is non-unital, and A plus is the asymptotic to the direct sum of A plus C. And how do we show this? I can just give you the isomorphisms and then one checks that this works. So it goes like this. So if I include that, just send any fundamental classes. It has this form. So A tilde is defined like that. So you define higher of A and so on identity. And if A is unital with any, let's say E to distinguish it from the complex numbers. So then you define A plus A collection C lambda to A plus lambda times E. And that's the isomorphism that one has. So we note here that unitizing goes well with maps. So if there's a homomorphism, then alpha uses alpha plus just by the plus of alpha of a, which is also star homomorphism. So that's the thing. Okay. Right. So before we move on, I had to mention something that I think I forgot. That comes from the Gafford-Nymark, for example, it comes from the Gafford-Nymark Segal representation. So I'll split it in here if we're going to K0. So I think is that one of the natural constructions that one has is that, of course, one would expect that matrices over a sister algebra has to be a sister algebra, and that's not obvious from the start. So if A is a sister algebra, then M of A is clearly a star algebra. Yeah, well, the involution first transpose and take the involution of each entry. But it's not clearly, I mean, it's not obvious that this is a sister algebra, but one can give it a norm. Why? Because one embeds a Hilbert space by the GNS construction, and then matrices embed into matrices of this, which can be identified with the bounded operators from each direction of each n times, and then we give Mn of A. The first one. So that's kind of a neat way of getting a sister algebra structure on this thing. Okay, and we're going to use this, of course, implicitly in the following. So now we want to, before going to comparison of positive elements, I want to do the comparison of projections, which is the motivating thing. No? So and the group. Easier. So, well, let's define what is the line environment. So if we have two projections, let's say P and Q, this is structure A, we say that P is Murray von Neumann. I'll write this for shorthand to Q if P can be written as B star and Q can be written as B star. Okay, so B is what is called a partial isometry. Okay, and this is the same. the right module generated by P is a small to the right module generated by P. Or the left module generated by P is a small to the left module generated by P. It's the same. It's the same thing. And actually, one could reduce this to idempotence and do the same with idempotence, except of not choosing V star and V star, V star V, but VW and WB. So one can do everything with idempotence. So what I'm doing here is algebraic and done for any ring, but for sister algebras it's more convenient for the theory to use projections. So we write the like this for Morgan-Newman equivalence. And now we want to extend this to matrices. So we first set infinity available to be the directed unity for matrices array, where we identify with left order. Okay. So that's not really a union. So it's a union. So it's like a union with quotient this relation. And if you know what an inductive limit is that's an inductive limit. Inductive limits will appear later, I'm sure. So this M infinity is non-unital. Even if it is unital, it is clearly non-unital star algebra. But it's not complete. Right? But still is closed under functional calculus for finitely many elements. So still, it's good enough for many things. Yes, because we'll take a given element, you can just put it into corresponding matrices, which we know is a sister algebra. So for local things, this algebra is good enough. If we complete it, the completion is sister algebra. It is called stabilization. Okay. And denoted, well, I mean, it's a bit unfair to say it's denoted. Equals, let's say, a tensor thing. Well, we won't go into tensor products, but that's a tensor product of A with the algebra of compact operators on a Hilbert space. But that's one way to think of it in this course is like the completion of this thing here. And later we will use properties that, well, of course, will be kind of hidden. Okay, so ya pasamos votados. Now we can extend the Morgan-Newman equivalence to M infinity of A. Or to A, that's okay. That doesn't make a difference, but I won't make the case for this here. Maybe one, I will mention something. So we can extend this Morgan-Newman to M infinity of A, simply by saying that we have P and Q here. Then these two guys are projections that belong to some common matrix size. Some n up to equivalence, and the Molar monomer equivalent to Q in infinity means that we can compare them in an array. And of course, one has to show that doesn't depend on which end you choose, but that's because the way things are constructed, everything works okay. This extends to here, and it also extends to the completion, and it really doesn't change anything. So every projection in the completion is equivalent to a projection in M infinity over here. That takes some work, but one doesn't lose information projection-wise from A tends OK or M infinity of A. For positive elements, the story is different. So that's why the Cuntz semigroup will make a difference between these two things. And we will see, I hope, later. Not today. Okay, so now we define the abelian to be the set of, so this projection, anything here. And what does this mean? This thing here is the non-algebraic equivalence class. So we take the set of equivalence classes of this, and now this thing is a monoid. So a monoid, which is a set with well, maybe I should say an abelian monoid. It is a set with an associative and commutative operation and a neutral element, so a zero element. So we have obviously addition, and this explains why we need to take all matrix sizes. So P belongs to some matrix size, Q belongs to some other matrix size. So then one takes this diagonal matrix, which is another matrix of projections, which is a projection again. And one has to check that this is the same as this, which is true. It's a question of writing down things, but it's not all work. And that has the name of the Morrey-von-Neumann semigroup or the projection semigroup, the projection monoid. And the terminology is not very fixed, but we call it the projection monoid or the monoid. Sorry. Well, so the semigroup business is a thing that I think comes from tradition. So semigroup, an abelian semigroup would be something which has a commutative and associative operation and doesn't necessarily have a unit. It's like a zero. So monoid always has a zero. So why do we call it semigroup? I think it's historical reasons. So it's called semigroup, even though it has a zero. So it should be called monoid. Like the Cuntz semigroup always has a zero. So it should be called Cuntz monoid, but anyway. Yeah. So now, so we have this thing, and from here, which is a monoid, so it doesn't have a group structure, there's a usual construction to construct a group out of this. Yeah. So the Grothendieck group construction right to the array gives an abelian group that we call G abelian. Okay, so right. So how does one construct this group? I will just indicate how it goes because groups will not be so important. I mean, we want to focus on the semigroup part. Because by constructing a group, I mean, we gain structure, but we lose information. We may lose information. But of course, we gain structure because abelian groups are better behaved than abelian monoids. So the way to construct this is just taking the array plus the array, pulling out an equivalence relation, and the relation is given by there's pair PQ is equivalent to a pair prime Q prime. So the idea is that I want to make so P and Q. I cannot make subtractions here, so I want to make differences of elements. So I want to make P minus Q and P prime minus Q prime. So this guy wants to be P minus Q. So this means that since it wants to be P minus Q and this has to do with this means that P minus Q prime has to be P prime plus Q, right? And because this B is not necessarily cancellative, so I might not be able to cancel from sums, one has to allow it for an extra one. So some projection on. That gives us an abelian group. And if A is unital, we define A0 array to be the Grothendieck group. Okay. And okay, what happens if A is non-unital? Well, if A is non-unital, things get a little bit more tricky. But to make the theory work, because we want to talk about K0 of an ideal, and we want everything to be to work consistently. So if A is non-unital, of course, one can do the same and compute G of A. That doesn't require a unit. Yeah. But for technical reasons, for what we want to do later, it is more convenient to take the utilization, and we take the natural map that goes from the utilization to the complex numbers, so that A quotient, A tilde quotient A is isometric to C, and define this array to be the kernel of the induced map to this. Okay, there's a bunch of things that are hidden here. So K0 is factorial from so I mean in general, but in particular for unital algebras, we need this to define this thing. So you have a map from these two unital algebras, then you have a map from here to here, and therefore I mean this map, and you can this is a group homomorphism, and you can compute it. This is also identified with the integers. One can show this basically by the rank. So you take projections in M infinity, so projections in MM, and you compute the rank. The rank is a natural number, and because you do differences, you get the integers. That's the basic idea here. So in particular, then K0 will be functorial in general. So given the ideal, close to say that we have a system algebra, and we have formula I, an exact sequence of this form. So you can take the ideal inside A and the quotient, and then we get K0 I, A0 of A. This exact thing in the middle. And what else? So K0 is also continuous. This will appear, I suppose, in a more general context later. K0 is continuous means it respects inductive limits. Okay. And finally, the menu will take break, sort of. What I want to say, yeah. So for V only, one cannot say, even if you have unit of everything, one cannot say that you have this same thing. So well, I mean, exactness for monads is not clear what happens, and so the situation is more delicate when one deals with just semigroups. We will see what happens with the full semigroup. And finally, I want to mention that D of A, just as a monoid, of course, any abelian monoid is what one can say is algebraically ordered. That's not particular of D of A. Any monoid can be algebraically ordered, and this means that you will find x was equal to y by definition in your monoid, even only if there exists a set such that x plus z is y. So two things compare if you can find a complement. Okay. But what does it mean, this order, in terms of the Murray-von-Neumann equivalence? Well, so what? That's why I bring this here to this picture. So P less than or equal to Q, this means that both have a projection in some matrices, such that when you do this, Q, and that's the same, that P is what is called Murray-von-Neumann, so equivalence to Q. And what is this? So by definition, this means that P is B star and Q is B star B, and B star B is less than or equal to Q as positive elements. So projection is positive, so this means that these two guys compare. So let us check that if you have this, then we can actually produce a complement, and the complement is similar. So if P is B star, B star B is less than or equal to Q, then we have R to be Q minus B star B. Okay. And then this thing is actually a projection. One can check it. This is a projection. Okay. Projection. And we have that P P plus this projection. Well, I have to do this thing here. And this actually is equivalent to Q. Yeah, because P, this thing here, P direction, well, I haven't said what that is, but this is by notation. This we will be using most of these notations quite a bit. So this is now P is B star, direction is B star B, and now this is equivalent to B star B, right? Because this is equivalent to this, we have some Q minus B star B, and now this is the same as Q, or so formal equivalent to Q. So P plus this guy is equivalent to Q. So we always have complements. And that will be a key difference with when we compare positive elements. Okay, so I think it's the right place to stop or break. Yeah. Oh, hay una pregunta. Okay. So I'll stop the recording.